Okay, so our next speaker is Francesco Pase. He's a lead AI research engineer at NEWTWEN. And he's going to tell us about his latest work, which is titled Adaptive Compression in Federated Learning via Site Information. So Francesco, the floor is yours. Looking forward to hear everything about this work.
Thank you, Albert. Thank you for having me. Let me share the screen. So thanks for having me. Today I'm going to present one of my last paper out of my PhD. And it's called Adaptive Compression in Federated Learning via Site Information. And this is actually, we will present this paper at ISTAT 24 in 1 month. And this is a joint effort with Pedivan Isaac and Professor Stanley Koyeko and Seki Weissman from Stanford University, Professor Dennis Gould from Imperial College London, and Michele Zorzi from University of Padua. So in this talk, I will rather focus on the details of the basically the algorithm rather than on implementation. That is more standard flower implementation of that. So we start with just this slide that probably all of you are familiar with, and all of you know. This is like usual federated learning kind of pipeline. I just use this slide to point to you where I focus with this research. So again, the idea is basically to have their clients to train local models by using their local data without sharing their raw data to the server, but just rather to send and to share the model updates or grading information to the server. And then the server can aggregate this information and produce a new global model to be broadcast back to the clients. Now, this work will focus on the communication efficiency of federated learning, especially if you think about wirelessly connected devices, for example. We may have some problems due to network resource constraint, or we may also have some battery constraints on the edge device. And we know that the communication part is also can heavily impact on the battery lifestyle of an edge device. So the idea is, how can we reduce the communication burden from the client to the server while performing federated learning in this kind of communication constrained environment or devices? So, of course, federated learning is becoming very popular, but the models are becoming huge. So this motivates somehow this research direction. You can think of, like, for example, also the flower efforts in implementing federated learning strategies for LLMs. These LLMs contains billions, if not hundreds of billions of parameters. And, these model updates and gradient updates, they have the same size as the model ones. So, of course, the communication bar is becoming quite a bottleneck. And the second observation is that the research literature is showing that models contain redundant information that usually it's not always so helpful in training such huge models. For example, you can see here just a few plots from this seminal paper on the lottery ticket hypothesis, where basically the idea is we can remove a lot of connections, so a lot of information from the model, but still having very good accuracy performance. Of course, now there are a lot of new works popping up nowadays on LLMs and other huge models, where basically the idea is to prove, or for example, to apply quantization, knowledge distillation to reduce the size of those models, and still preserving the accuracy. But third, a very important kind of observation is that many distributed learning strategies, for example, here there is a QHGD that is one of the kind of baseline for federated learning. That is a quantization version of stochastic gradient descent. The idea of many quantization or in general compression methods is to communicate stochastic samples rather than deterministic value. So what I mean by this is that you can see here on this very simple example, imagine we want to convey the value of just one coefficient of the network, and without all of the generality, let's keep in the 0-1 range. And let's say that the real value of the new update is 0.6. Now the idea is to quantize basically the range of possible values into a fixed and finite number of quantization levels. In this case, we have 5, we have 0, 0.25, 0.5, and so on. And if we have the new value as 0.6, the idea is not to send just the closest kind of quantization level, but rather to compute a probability distribution over possible quantization level, depending on the proximity of that point to those quantization levels, and then to draw a sample from these quantization levels and send that sample why we are doing this is basically because somehow in this way we can preserve the unbiasedness of the graded estimation done at the server side. So this is an important concept, and this is basically the idea behind our work. But before diving into that, I will just give a very brief detour of somehow information theory for communicating data. So usually what people in communication theory community use to model and to formulate the problem of communicating data, for example, like sending the updates from the client to the server, is we can think of the client as observing a sequence of random variables x1 up to xn, all distributed according to P of x. And the idea is that the client has to send this sequence of samples, for example, the sequence of new model updates to the server, by spending the minimum number of bits per symbol, that is the rate. So basically, we want to quantify the number of bits we have to spend per symbol, for example, per model update. We need to send a message to the server, and the server then has to decode this message in order to recover the exact same sequence X, for example, the model updates and the full model updates. Now, the question is, what is the minimum rate that we need in such a way that the server is able to decode exactly the same sequence of x1 up to xn? And could Shannon provide, of course, the answer to this question in the seminar paper, and where basically he showed that as n goes to infinity, so as the sequence becomes longer and longer, we can basically code a message such that h of x bits per symbol, we can send reliably this information to the server. What is h of x? Is the entropy of the distribution P of x, actually, that has this shape that you can see here. This is not important, but the idea is that this is a very fundamental quantity information theory. So the entropy of the distribution coming from these samples. But now the point is, as I said before, usually all these compression quantization methods, they're not sending deterministic values, but rather samples coming from some distribution. So maybe the right mathematical formulation, and we were inspired by Polka's paper on coordination capacity. Here the idea is, maybe we don't want the server to exactly recover the exact sequence of samples that can be observed by the client. But imagine that this x1 up to xn are the new deterministic updates of your model. Then what the client can do is apply some sort of quantization scheme like QHD that we briefly explained before. And by that, basically, the client can compute a probability distribution over candidate possible values for the new updates. And these are the y1 up to yn. That those basically new updates depend on the realization of the x1 up to xn that have the real value of your model. But now the point is that the task for the server is not to recover the exact same sequence of y's, but just to be able to sample according to a probability distribution that is similar to the one obtained by the client. So the goal for the server is to be able to sample those y's, so the new candidate values for the model updates, according to the same distribution the client can observe. Now, this problem has, again, if you want to convey such information to a server, the minimum is the mutual information between the two random variables x and y. That is basically the divergence between the joint and the marginal distribution. Now, what is the divergence is basically a measure that basically is a quantity that measures discrepancy between two distributions. So the closer they are, the smaller the divergence, and vice versa if they are far apart from each other. And this is important because this will lead to some key observation for our work, where basically the first important observation is that this mutual information somehow measures the dependency between x and y. So what I mean by this is, if the new candidate values, for example, those y's, does not depend so much from the new updated values locally, the real values x1 to xn, then there is no need to send information to the server. The server can just sample according to distribution P of y without knowing the realization of the x that is basically observed only by the client. So the rate is 0. It will be kind of clearer later why this is important. The second observation is that this quantity, so this mutual information, is always less than or equal to the minimum of the entropy of x, entropy of y. Why I'm telling this, because it's important, because if we want to use the standard way of communicating updates or data, that is the one that I showed in the beginning, we know that the minimum rate that we need to reliably send this information over some communication channel is the minimum of these two entropys. So it means that we can send basically the right task, and the right goal for us is to send those updates in such a way that the server is able to send all according to the new quantized level. And if we do this, then we can see that we can save a lot of network resources, because of course the mutual information is always less than or equal to this lower bound for communicating data. And third, the mutual information can be written also as the average over P of X of the K divergence, again, between what? Between the probability distribution over the Y's, which is the marginal over the quantized model updates, and basically this conditional Y given X. So what this means basically is that if we have a global distribution at this phi of Y, that we basically we interpret this as the global model that the server distributed at the beginning of each round, and we interpret the kind of conditional distribution P of Y given X as the distribution over the new update condition on the training iterations performed by the client locally. For example, condition on the data set acquired by the client. Then we can see that this mutual information measure indeed the average, basically gap between the optimized local distribution and the global distribution. So you can think of it as the information acquired by the clients locally during the local training stage, so the new knowledge acquired by the client. And this makes sense because we want to send no more, no less than this quantity. So basically, we just want to send the information that the new client is acquiring via basically the local training stages. So given this, basically we propose and design KLMization of inside information at this KLMS. And you can think of this as a new and independent block that can be applied on top of already existing strategies. So let's think, for example, of any kind of local training strategy. The idea is, as long as we can interpret or we can basically represent this new model updates by some distribution Q of K is the client kind of index, we can apply KLMS on top of this and sample a new message that can be sent to the server by spending at most K divergence between Q and P, kind of peak per new model update. And of course, there are some algorithms that are more fit for this kind of strategy, but all kind of quantization method can use this. All Bayesian method are can naturally use this, and other algorithms that I will brief with us later. So the key point is that we can represent the local knowledge acquired by the client via distribution P of K, and the global knowledge via distribution P that is known both by the server and also by the client. And then we implement some sort of important sampling style algorithm to create the messages. So basically to compress and to represent the local updates and send them to the server in a very communication efficient way. So let's assume that we want to send, for example, one layer of a neural network. This is just for brevity. It is just 8 kind of coefficients. So we have 8 coefficients we want to send to the server. What KLMS can do is basically to group these coefficients into also non-uniform kind of groups. As you can see here, we may be able to group the first 5 and then the last 3 of them. And by each group, basically KLMS will compute a message and send this message to the server. So why this is important? Because previous work only considered kind of uniform pairing of those coefficients in the network. But also in centralized setting, we did kind of slightly different approaches. But what we observed by performing some simulations, some experiments, is that the information, usually federated learning, is not uniformly distributed over the network and over the route. So what I mean by this, basically, you can see here that in this 3D plot, we measure this K divergence, so this discrepancy in the local and global knowledge. So basically, this is the information gain acquired by the client while training the local model. And we can see that this new information is not equally distributed over the layer of the network and also over the route. And it makes sense because in the beginning, maybe you start from a random model, you learn a lot by training your model, and then in the end, while you are converging to a good solution, that the information gain is lower. And also, layer by layer, we already know that, for example, the previous layer and the latest layers, they contain different kind of information. And so they are updated at different stages during the training loops, and also with a different kind of scaling factor. So this is important. So we are able to group together coefficients in the net. And you can think of this also as directly related to the rate that we use to communicate those updates. And this is the key kind of property of KLMS, that we want to send only the new acquired information to the server and not kind of send redundant information to congest the network. So how it works in practice? So how can we send these updates with just these few bits per parameter? So the idea is that to apply importance sampling, as I said, I will just briefly go through this. Imagine we want to send just one coefficient W. Both the client and the server, they share the global knowledge, so this distribution P, on the first coefficient, for example, of the network, and they also share some random C. So they can both generate the same sequence of samples, candidate sample for the first coefficient, imagine W1 up to WK. This is superscript to indicate candidate for the first coefficient. And then the client will weight those coefficients by applying these, basically these alphas, where each alpha is computed by using the local distribution Q divided by the global distribution P. Of course, this is not known by the server, but only by the client. We normalize those weights, and then we can take a sample from the new distribution pi, that is basically a distribution over the indices of this sequence. And then you obtain this K star, and the client will just send the index of basically the K star value to the server. Of course, we just spend log 2 of K bits because we have K possible samples. And so we can, with the log K bits, we can represent a sample within this sequence. And the server can then decode just by looking at the K star and take the K star kind of sample in the sequence. And that is the candidate value for the coefficient W in the network. This is kind of important sampling applied to this strategy. And there is, of course, a relation between the K's, how many samples you take per coefficient, and the accuracy of the estimation of the new updated server. And there are some theoretical results also in the paper that I will avoid to explain here. And with KLMS, as I said before, we have dynamic rate adaptation. So what I showed you before in that 3D plot, we also see here. So if we use uniform binning, you can see here we have a uniform kind of rate, meaning the number of bits per coefficient is fixed at 0.125. But the K divergence, actually the dotted line, is going down as the training basically rounds go on, because of course we are learning less and less information from the local updates. As while applying the adaptive kind of counterpart of KLMS, we are able to, not in the beginning, but then to match the K divergence. And this means that we are sending only the meaningful information from the client and to the server without any kind of network or resource wasting. And the bits allocation is optimized over layers and over the rounds of the whole training strategy. Now, what we did also, then we took this KLMS and we applied on top of many existing strategies, for example, FedPM, QHD. We have also the Bayesian counterpart QLSD, that is kind of QHD in the Bayesian setting, and also other, and we compare against other baselines. And as you can see here, we perform a lot of simulation by creating a new block, the KLMS block in Flower, and some other compression block in Flower. And then this is the kind of accuracy versus bit rate trade-off you can see. And you can see that if you take one of the baseline and you apply KLMS on top of them, the KLMS is able to push those points toward the top left part of the plot, meaning that you may be able to achieve the same accuracy, if not better accuracy, by spending less bits per parameter. And of course, these are IAD kind of scenario, but there are a lot of simulations and results in paper. And this is also for the Bayesian counterpart for QLSD. Here, as I said before, LSD or QLSD or any kind of Bayesian strategy naturally is that KLMS naturally adapt to this Bayesian strategy, because in this way we already have the Qs and the Ps. So the model updates in form of probability distribution, as well as the global model in form of probability distribution. So in this way, it should be like the optimal way of representing and coding the updates from the client to the server. As you can see again here, we can outperform QLSD in this simulation scenario. And with this, I just conclude my presentation. And I wanted to highlight that KLMS is a novel compression and coding module that can be applied on top of many existing strategies. It can improve the accuracy versus rate trade-offs, leading to very good accuracy, even in very communication-constrained environment. And we have numerical results you can find in the paper. And also in the paper, as I said before, basically you can find theoretical findings where we are just extending the importance centric performance as a function of K in the distributed scenario. And this is interesting for kind of federated learning, kind of new compression algorithms.
Okay, well, Francesco, I think this was a great talk, and I saw some super strong results in the previous 2 slides, so I definitely gonna take a look at the paper. I have 2 questions here from people. One, which I think will be maybe useful for a lot, is like in easy words, like for example, looking back at the KLMS coding scheme slide. One question that I kind of also echo, yes, is so the client, in the end, like in plain words, the client is not communicating weights to the server, right? Is it fair to say it's communicating like a distribution that the server needs to sample? And
so exactly. So the basically the subtle part here is that the client has to communicate a new weight update, right? But you can think of it as okay, the client is uncertain about the real value of the update because there is this quantization kind of stage. And so actually in practice, what is communicating is an index of a sequence. Now, the point is that the way the server can produce the sequence and the way the client weight those indices in the sequence is approaching the distribution Q that is only known by the client. So this is, so basically, if you think of it, when K is very, very large, when you sample according to this kind of file method, in the end, you can sample according to Q, even though the server does not know Q. So I don't know if that is...
would that sampling that the server does, it might not result, that sampling that the server would do, it doesn't necessarily result in the same result that the client has, but I guess if this distribution is sharp enough, it will, right?
Exactly. So in the end, if this K is finite, basically the sample the server can obtain is slightly different. So it's coming from a slightly different distribution from the one known by the client Q. As K is larger, these two distribution basically converge to the same distribution. But of course, as K is larger, the rate also is larger because this is the number of samples we need to use to code just one coefficient. And as you can see in log 2 bits is the size of the message. So yeah, exactly. So the server will use an approximate distribution to try to insert the one known by the client. And you can kind of tune this accuracy versus rate trade-off by, for example, taking more samples for each coefficient.
Okay. Then a follow-up question I think could be related to this is, how does KLMS cope with clients that suddenly get new data, let's say? Because I think a lot of the strengths of KLMS is as the magnitude of the gradients starts going down, so the models need to change less and less, it can really, how can I say, it really benefits from that. But if now there is suddenly some extra data, there is a huge jump in the gradient magnitude, is it going to... The bits explode, I guess, right?
Yeah, that's a good question. And actually, you don't see it maybe clearly from here, but the point is that if that happens, it means that now the k divergence starts increasing, as you said. And here, maybe in the first round, so actually what we do is, in order to adapt the size and the indices of each of the beans in the network to group together coefficient and create the messages, what we did is we start from some random guess. And then as you can compute the KL divergence locally with the global ones. And as this basically, if the rate is not good for each beans, what we do is we adapt the size and the indices of those beans, and we send these new indices from the server to the client once every kind of X iterations, depending on how they diverge. So what happens, what we saw is that in the beginning, maybe we adapt the position of these beans a few times, and then you don't adapt again because there's no need to, there's not so much difference between the gap of the beans locally and globally. But as you said, if the new data arrive, then maybe this gap is larger, for example, at around 60. For KLMS, that would mean that we will see a jump again, and because maybe in the first round you are suboptimal, and then after the first round those data has changed, maybe the server is informed about that, and so it will distribute a new kind of beans optimization. So basically, it will distribute the bean indices so they can group together kind of optimal coefficients, and so then we start decreasing again. So yeah, of course you will see. So basically, KLMS can adapt to this new distribution of the data, and but of course you will notice an increase in the rate and then decreasing again.
Yeah. Okay. Interesting. Sounds. This final summary of what you said kind of remind me to other non-related things like video codecs. When there is a change in the content of the video frame, there is a big spike on bitrate. When
exactly.
There is Okay, cool, interesting. Okay, I have one final question from Brian on Zoom. Is the source for KLMS available on GitHub? Yeah,
so we are kind of cleaning the repo, and it will be shortly be available on GitHub also because it is related to the conference paper. So yeah, you will find all the code on GitHub.
Okay, great. Then I think this is everything. Brian says thank you very much. So that's good. So thank you very much, Francesco, once again.